Hello guys, it's Dimitri again, here with another video, just describing the general, the intro to quantum mechanics. So first off, we're going to start off with what is a wave function. So basically, wave functions are going to be dealing with your entire time while doing quantum mechanics. So let me tell you what those are. So what a wave function is, it's something that contains information about a system. The system may be a particle or a particle like an electron. So let's just put that information in about about a system, i.e. a particle. So, and this wave function can be described using time and position. So we have here position and time. And this position can be in 3 dimensions like x, y, and z, or it can be in 1 dimension with just x, or 2 dimensions with x and y. So, going on to our next point, the wave function doesn't really have a meaning. It's just something we get information from, like momentum, velocity, stuff like that. And also, I believe is yeah, velocity. Oh, and energy too. So we just put in. It doesn't have physical meaning. So if you see a wave function like graphed, it will like we're seeing it. You're not gonna really get anything from it from the graph. Now but when you square the wave function, what you get is a probability density. And I think some of you guys took in organic chemistry, so you guys should know this. I believe from that. It's pretty much the same thing. So probability density, if you square it, you would get so absolute value squared will give you the probability density. Or you can get the composite conjugate if it has imaginary numbers in it. This would be and it has a probability density. Now I'll just say probability finding the system at Q and T. Now also you could integrate the probability density to get a specific area between two coordinates. So let's say if it was like between position would be 0 to 1, you can get the probability density within that area. If you integrate over all space, so I'll just put all space equals 1. This would give you a value of 1 if you were to integrate over all space. And this just means there's 100% probability of finding the particle. Now, if you guys can think about it like this, if I were to go between all space, so if I were to look, let's say here or here, let me just draw a picture right here. And this is a graph of the probability density. If I were to look here and here, I'm always going to find a particle no matter what. There's a 100% probability of it. That's what that's what this 1 means. It just means there's a 100% of finding a probability. And also, probability can be between 0 and 1. But when you integrate over all space, you'll always have probability density of 1. All right, we'll just say between 0, and 1. So between 0% and 100%. All right. And this also means if you were to find this to be true, also this means that the wave function is normalized. meaning that you can find it when you integrate overall space. That means that wave function is normalized. And I'm gonna go over normalization in later on. All right. All right. So let's describe what a wave function is. What a wave function must satisfy. So what a wave function must satisfy, it must not have multiple values at a variable. I'll just give you guys an example of that. 0, 1, and then we got here. So this is just a trial wave function that we have to see. It's not a valid wave function. Now think of it like this. There's multiple values on the x position that this has. So this cannot be a valid wave function. So a wave function must be like this, where it has where there's no multiple values at every x. So right here must be single value wave function. All right, now let's go on to the next one. It must be continuous, and its first derivative is continuous. It's continuous. All right, and let me show you guys an example of that. Let's say you have a graph of a wave function, and there's like an empty spot here. This would not be a valid wave function because there must be a value here. And let's say if we were to graph the second derivative of it, let's just say just another example, right? Let's say example one. Let's say another example. And this is the graph of the second derivative of the first derivative of the wave function of a different wave function. Oh wait. What I meant to say was this is a graph of a wave function of another wave function. That's what I meant. So right here, this wouldn't be continuous at all because at here, if you were to integrate, if you were to take a derivative of this, this would be an empty spot here. And because of this example 2 will see this would not be a valid wave function. And guys, I'll show you guys an example later on why that is. Okay, let's go for 3. And the probability, if you were to take the probability of it, at any the probability, it has to be less than infinity. It has to be finite at all coordinates, or when you integrate, and it has to be positive. So it has to be, probability has to be greater than 0, and it has to be between, as I said before, 0 and 1. Let's say probability between 0 to 1. All right, and the fourth, the limit as x goes to positive or negative infinity, or at the end of its boundary conditions. So let's go here. Is equal to 0, and that means as you go to infinity. So let me show you guys an example here. Oh. This decays and goes towards 0, or it goes exactly at 0, and that would be a valid wave function. Okay, now I have everything here. Let's see what else I could talk about. I'll talk about normalization in another video. Not that you guys need to know it like right now. You guys got to some general idea of it. So let me go over some examples. All right. Find out these functions make good wave functions. So I think I showed three examples. Yep. And I think that should be it. Okay. So let's talk about this. So whenever you're talking about what makes a good wave function, you have to always graph it. Graphing it is a long way. So let's talk about x to the negative x squared. Now I'm going to use my graphing calculator to see what this looks like. I mean, I know by head for my head why how it looks, but let me just make sure. All right. So if you were to graph this, it would show that this reaches 1 at 0, and then it just goes and decays. Now this fulfills everything here. It decays at positive and negative infinity because right here it approaches 0, and it's continuous. I can graph its second derivative also to see if that's continuous. So we take derivative of this. This will be f prime of x. And this is the chain rule. This would be negative 2x, which would be the derivative on the derivative of x squared, negative x squared. This will be e to the negative x squared. Times e to the negative x squared. All right, and it goes. Oh, there we go. It approaches. It goes up, then it goes down, then it goes here. So at these here, there's no open spaces. It approaches infinity. As you see, it's continuous. There's no open spaces here, and the probability is finite. So if you were to square this, the probability will always be finite. This will just be on top. I mean, not this. I mean, this will just be this look kind of the same, and the probability will always be finite here. All right, let's go on to the next one. And this will be that'll be a good wave function. I'll just say yes, just for good wave function. Now on to the next one, which would be sine of x. So I would just have to graph this only a few times. So let's just say at pi over 2. And this would be at pi, negative pi over 2. And this is at negative pi. We know that sine of negative pi and pi would be 0. And at 0 it would be 0. And at negative pi over 2, it goes to negative 1. So let's just say this right here is negative 1, and this here is 1. So this would be negative 1. This would go here, and then right here, and then this would go to 1, and then this goes to 0. So then it goes, oh wait, I messed up there. Okay. And then it goes to, okay. Now, you guys may think that this is continuous. It has to have multiple values, and but and but I mean, sorry guys, sorry. I meant to say, but as it goes to negative positive infinity, it doesn't approach 0. It's just going to repeat this pattern of going up, down, and up and down. So this would not be a good wave function because it doesn't decay towards 0. So it's just I'll just put not a good wave function. All right, let's see what else. So this will go over continuous and non-continuous for x equals 1. So let's just say at negative 1 and 1. And at 1, this would be 1. Oh, let me just, I should have put this a little closer. I'll just go back. Just want to be consistent with drawing it. There we go. All right, so then we have it at 1 and at 1. Now, a red flag here is if it just arbitrarily just changes like this, that means it's not continuous here. For its first derivative, it's not continuous, but it's by itself is continuous, but its first derivative isn't is not continuous. And if it was a parabola like this, then its first derivative would be continuous because it's like it's slightly changing and then it goes to zero and then it goes up. But this just like changes, like it just goes down and up. And I guys can prove it to you by graphing the absolute value of x. Now, to take the derivative of absolute value it's just a trick. You guys don't need to know this for quantum mechanics. I just want to show you guys the proof for it. So the absolute value of x is literally just is just the square root of x squared. And so when you take the derivative of that, so let's just say derivative of h, which would be, if we do the chain rule, this would be 2x, and this would be over, oh, it's like times 1/2 because of that, and then this would be over x squared. But we know this is just x over radical. Now I can just draw this here. Oh wait, sorry. This would just be, yeah, wait, I am right about that. I forgot to put the squared. And this would just be, because we know the proof, x over absolute value of x. Alright, now let's just put x divided by squared, and then x, there we go. And then we go to the 1/2 power. I'm just sorry, I'm on my graphing calculator right now. Yeah, we know that from here that this cannot reach I'll take it as simplified. This will not reach cannot go to 0, so there will be like an open spot here, and it'll just continue on. So as x increases, I believe it goes to, I think it just does, it's just a, sorry, it's just a weird way it's graphing on my calculator, but I'm just gonna just say that just doesn't, there's an open space on 0, meaning it's not continuous on its first derivative. And that's just a proof for it. You guys don't need to necessarily learn that, but it's just to guys help you understand why it's not continuous. Let me try to see if I can why isn't it graphing correctly? Oh yeah, that's why it's not graphing correctly. It is graphing correctly. It's just one. It just does this. Oh wait, there we go. It just does this, but then it just does. Oh wait, this goes because of the negative number. I'll go over here, and then this just goes right here. Because at 0, it's like 0 divided by 0. There's no value there. Alright, and I think that should be it. There's no other examples, but that's pretty much it, guys. If you basically just remember your rules that what a wave function must satisfy. Yeah, you must satisfy, and basically what a wave function is. And you guys are gonna learn about operators. You know how it contains information like velocity, momentum, position, pretty much all that stuff. We're going to use in the next video or the next lesson you guys are going to learn is operators are going to be ways you can extract that information. Now, if you guys have any other questions, just post in the comments and send me an email on my Stony Brook SBU. I think I put it in the description. But yeah, guys, that's the video, and thanks for watching.